The James Webb Space Telescope, JWST, is humanity's latest cosmic eye, reaching out across unimaginable distances and capturing light that has journeyed for over 13 billion years. This light, however, tells us more than just a story of time. It reveals the evolution of our universe, shaped and stretched by its ongoing expansion. As we peer back at the most distant galaxies, we are virtually witnessing an ancient era, moving closer and closer to the inception of the cosmos, the Big Bang. The Big Bang Theory, a foundational narrative of modern cosmology, boldly suggests that our universe had a distinct beginning and is finite in age. Yet, from its inception, this singular cosmic origin has been met with skepticism, and challenges to its validity persist even in mainstream cosmology. For decades, the Big Bang Theory held strong, especially after the discovery of the cosmic microwave background, CMB, in the 1960s. This background radiation, a faint all-encompassing hum across the universe, aligned perfectly with predictions of a hot, dense early universe. However, groundbreaking observations by the JWST in recent years have revived old doubts and raised new questions about the Big Bang's legitimacy. Through the astonishing clarity of the JWST, NASA's cosmic time machine, we've seen clusters of ancient galaxies far larger and more numerous than expected, challenging our understanding of the universe's earliest stages. As the telescope peers back to the time when the first galaxies formed, it offers humanity an unprecedented view, one that the Hubble telescope couldn't fully access. Hubble was simply not sensitive enough to detect the extremely faint redshifted light of these earliest galaxies. But with JWST's state-of-the-art capabilities, we're gazing all the way back to the brink of time itself. As we journey into this unknown territory, we come face to face with an age-old enigma. How did the first galaxies truly form, and does the universe as we know it really have a single, definitive beginning? The earliest universe was a hot, opaque place so dense that light itself could not freely travel. This means that no matter how powerful our telescopes, we cannot observe any further back with light. However, we are not limited to light alone. New technological advancements are opening the door to the detection of gravitational waves from colliding black holes, which could serve as a fresh avenue to peer back into the universe's infancy, perhaps even into the very phenomenon we call the Big Bang. The roots of the Big Bang Theory and its growing skepticism stretch back to the 1920s and 30s, when astronomers first observed that distant galaxies appeared to be moving away from us. This discovery, coupled with Albert Einstein's theory of general relativity, set the stage for the Big Bang model. Einstein's equations predicted that a static universe would be unstable, requiring either contraction or expansion. Observing this expansion suggested that galaxies must have been closer together in the distant past, implying an explosive beginning for the universe. The universe's expansion has several profound implications. Not only do objects move farther apart, but the light emitted from them stretches, shifting to longer wavelengths as time goes on. Since wavelength corresponds to energy, with shorter wavelengths being more energetic, this redshifting means the universe has been cooling as it ages. By rewinding this cosmic expansion, we reach a point where everything would have been so hot and dense that neutral atoms couldn't exist, leading to a uniform, searing hot glow. This glow was confirmed in 1964 when astronomers Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, a pervasive radiation field faintly echoing the universe's fiery origin. Yet, as the JWST pushes the boundaries of cosmic observation, scientists are discovering features in the early universe that strain the traditional Big Bang narrative. We see vast, luminous galaxies where there should be none, clustering in ways that defy expectations. So, if the Big Bang Theory alone doesn't explain these anomalies, what else might? At the heart of the Big Bang Theory lies a singularity, a point of infinite density and temperature where the laws of physics break down. This is where space and time supposedly begin, but this concept, while powerful, has limitations. Imagine trying to describe the entirety of existence compressed into an infinitely dense point. This is where our understanding hits a wall. Even though many aspects of the Big Bang model have been supported by observations and laboratory experiments, this initial singularity remains an enigma, begging the question: could the universe have had a different kind of beginning? In its journey to understand the cosmos, science has found ways to recreate similar conditions. Quark-gluon plasma, for instance, has been synthesized in laboratories, and matter-antimatter pairs have been produced to align with early universe predictions. Through these experiments and by analyzing the cosmic microwave background's fluctuations, we have a well-supported picture of the universe's evolution. However, significant mysteries remain. For example, if all regions of space were once compressed into a single point, why do we observe such uniformity in the universe's temperature? By traditional models, areas of space should display varied temperatures since they wouldn't have had time to exchange energy or information. Additionally, we might expect to find remnants from the hottest epochs, such as magnetic monopoles or spatial irregularities, yet none are observed. These discrepancies open the door to new possibilities. Either the universe inherently possessed these balanced properties from the outset, or there was some mechanism that imposed these conditions. One candidate explanation is cosmic inflation, a rapid expansion theorized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed a revolutionary idea. He theorized that before the hot Big Bang, the universe experienced an exponential expansion. This inflationary phase could explain why the universe appears flat, homogeneous, and isotropic. After inflation, the universe would transition into the hot, dense state associated with the Big Bang, setting the stage for galaxies, stars, and planets to form. However, as scientists now realize, even cosmic inflation does not resolve every anomaly. For example, groundbreaking observations by the JWST have revealed surprisingly large galaxies from the universe's infancy, suggesting an accelerated formation rate that inflation alone doesn't explain. JWST's incredible capabilities offer humanity an unprecedented glimpse into the cosmos. This $10 billion infrared telescope has captured breathtaking images of the early universe, revealing an array of massive, luminous galaxies from when the universe was only a fraction of its current age. While astronomers previously believed they had a solid understanding of how matter coalesced to form the first stars and galaxies, the JWST findings suggest a much more rapid evolution than expected. These observations have stirred excitement and caution among scientists, as some theorists are compelled to revisit fundamental assumptions about galaxy formation. According to astrophysicist Erica Nelson, massive galaxies observed within the first 500 million years of cosmic history defy existing models. The JWST's preliminary findings indicate that galaxies in this early epoch may be far more massive and numerous than previously thought, potentially housing masses comparable to today's large galaxies, like the Milky Way. This rapid growth challenges current cosmological models, which propose that a galaxy of such size wouldn't form until 1 to 2 billion years after the Big Bang. Nelson's research suggests that galaxies may be growing more aggressively than anticipated, leading to the possibility of new theoretical frameworks for galactic evolution. Dark matter, an invisible and mysterious substance, is thought to make up about 85% of the universe's mass, shaping the large-scale structure of the cosmos. Conventional cosmology suggests that galaxies form within massive halos of dark matter, which gravitationally draw in ordinary matter, allowing stars and galaxies to coalesce. Yet, JWST observations challenge this model, as galaxies appear to be forming in ways that defy our understanding of dark matter distribution. The presence of dark energy, an equally elusive force responsible for the universe's accelerated expansion, further complicates the picture. Some models suggest that early dark energy, a temporary boost in dark energy density, could have accelerated galaxy formation, potentially aligning with JWST's findings. However, such adjustments must reconcile with the broader framework of the standard cosmological model, which has successfully explained cosmic evolution on large scales. As compelling as the Big Bang theory is, it's not the only explanation for the universe's origins. Several alternative theories have gained attention, each offering unique perspectives. The quasi-static state theory, unlike the Big Bang, suggests a universe without a beginning, where matter continually appears as the universe expands. This theory proposes that, as galaxies move apart, new matter is generated, preserving a uniform density. However, it failed to account for the CMB, which strongly supports a hot, dense early universe. The mirror universe theory, a more speculative concept, posits that two universes were born in the Big Bang, one moving forward in time and the other backward. This twin universe would evolve in reverse, providing a mirror reflection of our own cosmic history. Though highly hypothetical, it suggests that the universe could be more complex than previously imagined. The digital simulation hypothesis raises the possibility that our universe is a simulation crafted by an advanced civilization. Quantum entanglement and the peculiar nature of spacetime lend some conceptual weight to the idea, although it remains unprovable. The simulation hypothesis touches on questions of predestination and reality, challenging our understanding of existence. The multiverse theory, a popular alternative, suggests an infinite number of universes, each with its own physical laws. According to this model, dark energy fluctuations trigger multiple Big Bang-like events, producing a vast multiverse, while our universe expands, creating a void of dark energy. This model implies a continuous cycle of creation, collapse, and rebirth. Each of these theories offers unique insights into cosmic origins, posing new questions about the nature of spacetime and matter. While the Big Bang theory remains the prevailing explanation, it has been challenged and reshaped by new evidence and fresh perspectives. The JWST, with its unparalleled sensitivity, is poised to unlock even more secrets of the universe. As the telescope continues its exploration, it may uncover answers that reshape our understanding of the cosmos and perhaps even point toward a radically new origin story. The James Webb Space Telescope, JWST, has revolutionized our understanding of the cosmos, providing data that is forcing scientists to rethink foundational theories. Its discoveries are reshaping our understanding of the universe's evolution and pushing the boundaries of what we thought was possible. While many of the phenomena observed by JWST align with established cosmological models, some findings suggest that we might need to rewrite the textbooks. The discovery of incredibly massive galaxies formed only a few 100 million years after the Big Bang challenges the conventional timeline for galaxy formation. In existing models, galaxies take longer to form as they gradually accrete gas and dust over billions of years. However, the observation of massive, mature galaxies in the early universe suggests that galaxy formation might have been far more rapid than previously thought. Some scientists speculate that these early galaxies could have grown quickly due to the influence of dark matter or even dark energy, substances that are still poorly understood but whose effects seem to be becoming more crucial in galaxy evolution. In addition, JWST's findings have prompted new discussions about the nature of dark matter itself. While dark matter was theorized to be responsible for the gravitational pull that holds galaxies together, JWST's observations have suggested that galaxies could form and evolve in ways that do not fully rely on dark matter as previously thought. This has led to questions about whether the nature of dark matter is different from what was assumed, or if new, yet-to-be-discovered forces are at work. Furthermore, some researchers are looking into the possibility that dark matter could be more localized than previously assumed, clustering in areas of the universe with vastly different structures than we imagined. Similarly, the concept of dark energy, the mysterious force driving the accelerated expansion of the universe, has faced new scrutiny. While dark energy was once assumed to be uniformly distributed, JWST's high-resolution observations are beginning to show subtle variations that could change how we perceive the universe's expansion. Could the effects of dark energy be evolving over time, or perhaps behaving differently on smaller cosmic scales? These questions are challenging cosmologists to refine their models and consider new possibilities about the universe's fate. Moreover, JWST is unlocking new insights into the formation of the first stars, or population 3 stars, which are believed to have formed from the primordial hydrogen and helium left over from the Big Bang. These stars are thought to be massive, hot, and short-lived, and they would have been responsible for the first generation of heavy elements through nuclear fusion. However, JWST has revealed evidence suggesting that stars could have formed under conditions far more varied than previously thought. The size and composition of early stars may have been influenced by factors such as radiation from the first galaxies or the early expansion of space itself. This challenges traditional theories about stellar nucleosynthesis and suggests a more complex narrative for the early universe's evolution. Another intriguing aspect of JWST's data involves the detection of large-scale structures in the early universe, such as the first supermassive black holes. According to existing models, supermassive black holes should have taken much longer to form, but JWST's observations of young galaxies seem to suggest that these enormous objects were already in place within a few 100 million years of the Big Bang. How these black holes came to be so massive so quickly is still an open question. Some scientists hypothesize that black holes could have formed from the collapse of large clouds of gas, while others suggest that the merger of smaller black holes or the direct collapse of dark matter could have played a role. The presence of these early black holes raises the question of whether they were essential for the formation of galaxies, as their immense gravitational pull could have played a crucial role in shaping their structure. In terms of cosmic evolution, the JWST's detailed observations of the early universe are beginning to provide hints that cosmic inflation, although an important part of current cosmological models, may require refinement. Inflationary models suggest that the universe underwent an exponential expansion immediately after the Big Bang, explaining the uniformity of the cosmos. However, the discovery of structures like massive galaxies and supermassive black holes in the very young universe could point to an inflationary process that was even more complex than previously thought. If inflation occurred in different ways across different regions, it could help explain some of the anomalies in the distribution of galaxies and matter. Furthermore, JWST's ability to capture data across different wavelengths of light is revealing a new level of detail in the distribution of cosmic elements. This data suggests that the composition of early galaxies may not have followed the patterns anticipated by existing models. Instead, the presence of certain elements in unexpected quantities might imply that chemical processes in the early universe were more diverse than once assumed. This opens the door for new theories on how the first elements were created and distributed. As these discoveries unfold, the implications for our understanding of the cosmos grow even more profound. The Big Bang theory may not need to be discarded entirely, but it's clear that the narrative of the universe's origins is far more complicated than originally believed. In the wake of JWST's revelations, cosmologists may soon find themselves revising not just the details of the universe's past, but the very frameworks that govern our understanding of space and time. Whether through the continued exploration of the early universe, advancements in theoretical physics, or entirely new observational techniques, the journey to uncover the true story of the cosmos is far from over. Each breakthrough brings us closer to comprehending the vast and mysterious origins of everything we know.